Hey everyone, how you doing today? My name's Myles, and today I'll be presenting my undergraduate dissertation. It was on upgrading Gin's profiler to the current Java version. My name's Myles, and I worked on this with Sandy Brownlee from the University of Stirling. So first off, I'll give you the kind of structure of the presentation. So first I'll be explaining what Gin actually is. Then I'll be going through kind of the role that a profiler plays, then how I selected a profiler, how I tested it and experimented with it to make sure it was the proper one, and then kind of concluding and looking at the results and kind of the things that I did. So first off, what is Gin? So Gin is kind of a toolbox for genetic improvement. So we all know TensorFlow. So imagine TensorFlow, but for genetic improvement. So it's made to be easy to understand, lightweight, easy to build on. So you have a research team and you want to do research in genetic improvement, rather than you writing your own framework and you spend 6 months writing this framework, you can just start with Gin and build up from there. So it kind of implements all of the kind of common things you'd see in a genetic improvement framework. So edits, testing, profiling, memory measurement, things like that. How genetic improvement in Gin works. So first, you take a piece of code, and then at random we make mutations to that code. So that might be, we delete a line, or we delete a function, or we swap two functions, and that gives us a number of mutated pieces of code. So these mutated pieces of code we call the search space. We search through these kind of mutated code, and what we'll do is we'll check if they compile, we check if they run, and if they run properly and produce the output that we saw before from the test cases, then we can say they all work. And kind of the final step is to see if they are faster. So obviously the point of Gin is to give some kind of runtime improvement to code. So if this code works and runs faster, then we can say it's kind of a correct mutation, and we can iterate on that mutation further. So we see here that this far right kind of blue piece of code, we've said that this is a working piece of code that offers a runtime improvement, so we're going to iterate on this further and edit this piece of code further. So the problem with Gin is it's stuck in Java 8. So there were kind of two problems with this. So the HProf profiler, so HProf only worked in Java 8 and below, and the reflection security. So we kind of fixed reflection with a bit of a workaround, but the profiler, we were a bit more careful with it. So we basically wanted to get Gin into Java 9 and up. So why did we have to be careful with the profiler? Well, the profiler is sort of, in a genetic improvement framework, the importance of it is selecting what we call hot methods. So let's say you have 100% of the code. You have a code base and you want to edit 100% of the code. So let's say we make 4 edits and at 100% of this code. Well, one of these edits might make it a lot faster and the other 3 might make it a little bit faster. How do we decide kind of how to shorten this process, how to speed it up a little bit? Well, let's say if one of our functions runs for 10 times longer than the others, obviously we want to edit that function. We don't really want to spend too much time editing other functions. So what our profiler does is profiles the whole program. We run all of its unit tests and we find where the CPU spends most of its time. So if the CPU spends most of its time on 10% of the code, then we don't really have to edit 100% of the code. We can just focus on that little 10%. So that's what our profiler does. We profile the program first, all of its unit tests, so we can find a list of its hot methods, and then we target those hot methods for edits. And that, in turn, kind of cuts our search space down a lot, so speeds up the kind of genetic improvement process quite a bit. It also determines the order the hot methods are ranked in, so we kind of want our profiler to work similarly. If, HProf, we used that before, we want to get similar results with the new profiler. We want to be getting similar ranks in our hot methods so that we're targeting our edits at the correct functions. We also need to consider how the profiler kind of plugs into Gin and is used by it. So HProf was very easy to plug in and very easy to use, so we don't want something that's too complex. So kind of using all this information, I dotted down some criteria for selecting a new profiler. So just as I said before, HProf was very, very simple to use. It was just kind of run with some command line flags in Gin when we run a program. So it should be, a new profiler should kind of run similar to this. And this kind of bottom little bit of text here is kind of the HProf output that we were seeing. So the thing that we're kind of most concerned about is this far left, the rank. So that's the kind of rank 1 means this method was seen on top of the call stack the most out of all of the methods in all of the test cases. And then we kind of care about the name of the method as well. So what would we do with this information? Well, we'd say rank 1, and we've got this checkboard. Well, we can kind of assume that checkboard is the longest running function. So if we want to make some kind of edit to any part of the program, we want to focus on checkboard first. This is where if we are editing this, we're going to get the biggest kind of runtime improvement if we can speed that function up. And then next is obviously rank 2, and then rank 3, and then rank 4. So we care a lot about kind of the order we get these hot methods in. If we, just got a kind of random order, then, we wouldn't be throwing edits in the right place, and it might take a lot longer to speed up this program a reasonable amount. So yeah, we want to get kind of a similar output to this with our new profiler. A few more kind of criteria. So input and output needs to be handled automatically. Obviously, this is a genetic improvement framework. It runs automatically. You plug your program in, you run Gin, and it works its magic. We shouldn't need a kind of researcher or a user to manually be putting in hot methods or manually be checking output. So there shouldn't be kind of a visual interface to our new profiler. Again, low overhead is needed, so we run all of the test cases for a program to profile it. For some, big programs, this might take hours and hours. If we're doubling the time or even adding 50% of the time, it's kind of an unacceptable amount. So we need very low overhead with our new profiler. Gin is, it's a research tool. It's not meant to, have 100 dependencies or cost any kind of money. So we're not going to choose an external profiler that costs, has a subscription with it. Also, HProf is packaged in with JDK, so it was very easy. People didn't have to download external dependencies to use this, so we kind of want to keep that the same with this new profiler as well. As I said before, the profiler is quite, it's an important part of the framework, so it does need to be accurately counting the running functions from the code base. So, like I said before, we're more concerned with the rank that we get these functions out in. So we want something that gives us similar ranks and functions to what HProf did. Some candidates. So I went through and I looked online at what kind of Java profilers are available, and using our criteria from before, I kind of cut some out and kind of selected one. So obviously, as I said before, visual interface, this is a big no. We can't have something that requires kind of manual work. So this kind of takes out Visual VM, Java Mission Control, and the NetBeans profiler. They all use very kind of they're not really for automatic use. They're more for manual. You look at the screen, you check it, a user checks it, which we don't really want. A cost associated, JProfiler seemed like a really good candidate, but there is a subscription associated with that, and we don't want users paying to use Gin. Large overhead. So JConsole in the Oracle documentation, it actually specifies that you shouldn't use JConsole for larger scale profiling. It says it's very adds a lot of overhead. So obviously we didn't want to use that one. So this kind of brought us down to one good potential candidate, which was Java Flight Recorder. So this is what I went with and kind of went through the next steps with. So integrating JFR into Gin. So before I could run any experiments or do any tests, first we had to put JFR into Gin as HProf kind of worked in Gin. So there are a few key differences that I had to work out first. So as we saw before, HProf outputs that handy little text file. JFR does not have kind of a text file that it outputs. It just outputs this .jfr file, and the next point kind of gives us the differences in these files. So HProf pre-processes the data and just gives us the most commonly seen methods on top of the call stack. So HProf obviously gave us that nice little document with the ranks and the method name. JFR doesn't give us that. It just gives us a list of the call stack traces that it sampled. So what we have to do is we have to manually process those. So where HProf does that processing itself, we have to look through these call stacks and say we have to kind of do that processing ourselves. So HProf seems to skip Java language functions. JFR contains all of these Java language functions. So when using JFR, it's not as easy as just saying, okay, what's on top of the call stack? We do have to do a bit of a bit of processing. HProf profiles all threads. JFR doesn't profile sleeping or waiting threads. It also doesn't profile kind of JVM specific calls, so things like raising exceptions or what we'll see later, system calls, so checking the system time. It can't see calls like that. So I did mention about processing the call stack. So HProf obviously pre-processes all of these call stacks. It gives us a very clear kind of view of what's running in the program. JFR just gives us the call stack. So if we see a call stack like this, we kind of have to ask, what part do we actually call about? Well, the top two functions here are kind of just Java language or Java utility functions. We can't edit them, so we don't really care about them. So we look at the top of this call stack, we say, is this part of the main program? We can do that by checking the package name. So we say, this is a Java program, we don't care. We jump to the next one. This is a Java language function as well, we don't care, we jump to the next one. And this package is main program, which is our main program we're processing, so we do care about this. So we're going to say that this main program.begin is on top of the call stack. So yeah, that's how we're processing our call stacks with JFR, kind of manually. Next, so after I kind of got it all working and put it all together, I decided to run some experiments. So first, I profiled a set of kind of functions that calculate primes, and next was to profile a more realistic program. So first, profiling prime number calculation. So why did I choose to do this? Well, it was kind of very easy to see, as we were looking before, we care about the ranks, and it's easy to tell that a function that calculates 5,000 primes should be ranked lower than a program that calculates 25,000 primes. So what we're expecting is we should see the ranks should be 25,000 should be first, then 20,000, then 15,000, then 10,000, then 5,000. So it's kind of easy to say that, and we have the results that we expect before we kind of run that experiment. So these are the results. So what you've got here is the primes found on the far left, the time taken, and then the samples we're seeing. So both href and JFR have a sample frequency of 10 milliseconds. So obviously we're expecting that if the time taken is 20 milliseconds, we're expecting 2 samples from both of the profilers. What's interesting is JFR kind of consistently gets less samples than href does. href, it gets a few, but it's always kind of a little bit behind what we expect. For this 20,000 primes, we're expecting 26 samples, we get 23. It's a little bit off. Maybe there's a bit of noise or a bit of stuff happening in the JVM. So maybe we're not seeing the full picture, but JFR gets almost half the amount that we're expecting, which is strange. So this is kind of something that we saw over a lot of experiments. So I decided to kind of note down some reasons maybe why. Obviously, as I mentioned before, href runs in Java 8 and below, whereas JFR runs in Java 9 and above. So we did have to run the program on different Java versions for each. Although when we had a look, we had a look at the average runtimes, and there's almost no difference between each version. So it can't really be that we wouldn't be seeing, this much of half as many samples from the JFR profiler just because of this tiny difference in runtimes over versions. Thread in a state not profilable by JFR. So obviously JFR omits samples if the thread is kind of in some kind of a waiting or a blocked state, although it's a single-threaded program. So it's kind of, I'm unaware of where this thread would ever wait. I guess the final thing, and something I realized in this next piece of investigation, so we look at this code, so we know that this code is going to run for 2,000 milliseconds. We're checking, and we're running this while loop until 2,000 milliseconds hits. href sort of consistently returns 127 samples, whereas JFR returns between 10 and 30. It's a bit weird. We're getting way less samples with JFR, which is weird. Although, when you have a look, the really only thing this while loop does is put the system in current time in milliseconds into now, and it checks if it's sort of been more than 2,000 milliseconds. So this call here, system.currentTime in milliseconds, JFR actually can't profile this. So what happens is we make this call to the system.currentTime milliseconds. It does some kind of input and output from the JVM. It checks the current time in the system, and then it returns back. So when this happens, JFR can't profile that thread, which means because this is the longest running thing, we actually never see really this function. So we can only profile this function when we're in this while loop, checking if now is less than 2,000. That's the only time we can profile this function. So that's why we get so few samples with JFR. I kind of decided we can live with this. Obviously we care more about the rank, and what we saw before in our results is that the ranks were pretty much lined up. We had the 30,000 prime function, higher rank than 25,000, that was higher than 20,000, and it was all in order. So that's what we care about more than sample amounts. Next was kind of to profile a more realistic program. So I profiled Spark, a Java web framework, not to be confused with Apache Spark. The standard GIN interface was used, ran Spark's unit tests, and produced a hot method summary. So this is the results. It might look a little confusing, but what we're seeing here, each blue dot is a JFR method. So first we profiled the program with JFR. We put in the average number of samples and the average rank for each method, so that's the blue dots. And then we profiled the program with hprof. So every time we saw a function with hprof that we had seen with JFR, we plotted it as an orange dot. So what we care about here is kind of, and these coefficients on the side, is the correlation between JFR functions that we saw and the corresponding hprof function. So maybe a function might be begin program. If we saw that with JFR and it was in rank 1, and we saw begin program and it was had an average rank of 3 with hprof, then we could say, they're sort of correlated, but they're not exactly the same. So for the top 10 JFR methods that we saw, the corresponding hprof methods, we had it was kind of a corresponding coefficient of about 0.3. So not super correlated in the top 10 JFR methods and their corresponding hprof methods, but in the top 20 JFR methods to their 20 corresponding hprof methods, there was a correlation coefficient of about 0.8. So we can imagine that as in the top 20 JFR methods, we're seeing the hprof methods in similar ranks about 80% of the time. So I think this is pretty good for our framework. It doesn't need to be exactly the same, but as long as we're getting kind of similar rankings for our functions and we're getting reasonable kind of results, that's what we need. We don't really care a lot about if we're getting the exact same ranks or the exact same number of samples. We just care more about getting kind of similar ranks, so that we're not wasting a lot of time profiling or editing things that aren't going to have a big effect on our runtime. So yeah, this is kind of the final results. I decided that this JFR would be reasonable as a replacement profiler, and now it is actually integrated into Gin. So some kind of conclusions from the research. So it gave an overview of the importance of a profiler. So we said in a genetic improvement framework, it's important to not just throw edits anywhere. Obviously, if you're editing 100% of the code, this is a huge search space. So it's going to take a lot of time to kind of run this code, test it, make sure it works the same, make sure it compiles. It's going to take a lot of time. So it's important to have a profiler that can select methods that take up a lot of the CPU's time. I proposed a set of criteria for selecting the profile and then ran some experiments to compare the two, the new profiler and the old. I think it was interesting to have a look at how that they didn't work the exact same. Maybe when we're selecting a profiler, we think hprof and JFR, they should work the same. We should just be profiling Java methods. But when we kind of run these experiments, maybe due to random noise or the way they work differently, we were actually getting different results. So it was interesting to look into that, not every profiler is built the same and they don't all work in the same way or give us the same results. So now, as I said before, JFI is integrated into Gin, and Gin works in the current Java version. And I think this was important to kind of retain its efficacy as a research tool. Obviously, if something like TensorFlow didn't work with current versions of Python, it wouldn't be very useful. So, or current versions of any kind of language, it wouldn't be very useful. So, I think it's important to kind of retain Gin's efficacy. So it's good that it kind of works in the current Java version. And that's my question slide. Thank you very much.